An alternative class of algorithms to the variable elimination algorithms is the class of message passing algorithms. And as we'll see, this is a class that is in some ways closely related to variable elimination, but also offers us additional flexibility in how we do summation and factor product steps so as to potentially come up with lower complexity than would be required by even the minimal elimination ordering. So let's consider a simple Markov network of the following type, and let's assume that I don't want to go to the cost of eliminating variables, although in this network it's not going to be too expensive. And instead what we're going to do is we're going to construct what we call a cluster graph. A cluster graph is something where is a data structure in which we're going to take little bits of knowledge from this graphical model, and we're going to place them in things called clusters. So here we have 4 clusters. In this example, cluster 1 is a cluster whose jurisdiction of influence is the pair of variables A, B. Cluster 2 has jurisdiction over B and C, 3 is over C and D, and 4 is over A and D. And these clusters are going to sit there and they're going to talk to each other, and they're going to try and convince each other that what they think about a variable that they both consider to be under their jurisdiction is correct. So for example, cluster 1 is going to talk to cluster 2 about the variable B, and it's going to tell cluster 2 what it thinks about B so that cluster 2 might become more informed about the distribution over B. And so what we're going to do is initially each cluster is going to have its own little piece of information. So phi 1 is going to go here, phi 2 is going to go there, phi 3 goes there, and phi 4 goes there. And now the variables are going to communicate with each other via these things called messages. So we're going to call, we're going to slightly rename things. We're going to call the variable, the initial set of beliefs, if you will, or evidence that a cluster has over the variables in this jurisdiction, we're going to call those psi's. In the example we just had, psi's were just the phi's in the original model, but as we'll see, sometimes it becomes a little bit more complicated than that. So now, the cluster 1 has the factor psi 1, and cluster 2 has psi 2, and so on. And now let's imagine that psi 1 wants to send a message. The cluster 2 wants to send a message to cluster 1. So it has to figure out what it believes, and a priori we're going to assume that it's just we're going to start out by initializing with a totally uninformed message. So, because initially they haven't even started talking to each other. So all messages are initialized to be 1. But now cluster 2 can come back and say, okay, I'm going to take the information, uninformative as it was, that I got from cluster 2, and notice that I call this message delta 2, 1. Delta 2 being the from, and 1 being the to. And so I've taken delta 2, 1, and now factor 1, cluster 1 is going to say, well, I'm going to take that, I'm going to multiply it with my current thoughts about the variables A, B, and that's going to give me a more informed factor. And now I'm going to communicate that information to cluster 4. But cluster 4 doesn't care about cluster 4 doesn't care about B. And so what I'm going to communicate to cluster 4, which is this message delta 1, 4, from 1 to 4, is the sum over B, which is the variable that 4 doesn't want to hear about, of the incoming message times my initial beliefs, or my initial factors. Now, this general process is what keeps the message passing algorithm going. So each variable, each cluster is going to send messages to its adjacent clusters that reflect this exact same process. So for example, just to take a different example, here is delta 3, 4. So this is the message that goes from 3 to 4. And that message takes into consideration the evidence that 2 sent to 3, which is this guy over here, times whatever 3 thought about CD to begin with. Notice, and this is important, that the message that 3 sends to 4 doesn't take into consideration the information that it got from 4. So there isn't, in this expression over here, the contribution of delta 4, 3. Because you want to avoid this case of, I repeat back to you a rumor that you just told me, and we all become more convinced about the truth of this rumor because, oh, I thought about this first, but now you're reinforcing me by telling it to me again, and the beliefs are just going to go up and up and up. And so what happens here is that we deliberately only restrict attention to evidence that comes in from other sources. So 3 only uses evidence from 2 when reporting to 4, and it only uses, conversely, evidence from 4 when reporting to 2. And so now this defines a communication protocol by which one cluster rather in the graph can communicate information to its neighbors. What do we do with this? So how do we generalize this message passing process? Let's construct a more general version of this. So this uses a data structure called a cluster graph. A cluster graph is an undirected graph whose nodes are not variables anymore. This is not a graphical model of the type that we've seen. The nodes in this undirected graph are clusters that correspond to subsets of variables, just like we had before. And we're going to connect to adjacent two clusters, Ci and Cj. And this thing called a subset is the variables that they choose to talk about. And clearly, each one can only talk about variables that it knows about, which is why the subset Sij has to be a subset of both Ci and Cj. So once again, Ci is the jurisdiction of cluster I. These are the variables that it understands. And Sij is the communication between two adjacent clusters in the cluster graph. So now given a set of factors phi, we're going to initialize the model by giving each cluster in the graph a certain amount of information. So each of my initial factors phi k in my graph is going to be assigned to one and only one cluster. And this is important. It needs to be at least one so that the information is taken into account somewhere. And it shouldn't be more than one because if you give it to more than one person, to more than one cluster, you're going to double count the evidence. They're each going to think it's an independent piece of evidence and it's going to be counted twice. Now, where do we put the information corresponding to a factor k? We put this only in we can only put it in a cluster that understands every single variable in that factor. So if we have a factor whose scope has a certain scope, that scope better be a subset of the variables that the cluster understands. Because otherwise it can't even talk about those variables. Both Ci and Cj. So once again, Ci is the jurisdiction of cluster I. These are the variables that it understands. And Sij is the communication between two adjacent clusters in the cluster graph. So now given a set of factors phi, we're going to initialize the model by giving each cluster in the graph a certain amount of information. So each of my initial factors phi k in my graph is going to be assigned to one and only one cluster. And this is important. It needs to be at least one so that the information is taken into account somewhere. And it shouldn't be more than one, because if you give it to more than one person, to more than one cluster, you're going to double count the evidence. They're each going to think it's an independent piece of evidence and it's going to be counted twice. Now, where do we put the information corresponding to a factor K? We put this only in we can only put it in a cluster that understands every single variable in that factor. So if we have a factor whose scope has a certain scope, that scope better be a subset of the variables that the cluster understands, because otherwise it can't even talk about those variables. So, once we've done that, see if I can erase this. Okay. We can now define the initial beliefs of a particular cluster as the product of all of the factors that are assigned to it. Now, some clusters might be assigned one factor, in which case psi is just equal to that phi. That was the case in the example that we just saw. Some clusters might have several factors assigned to them, in which case we need to multiply them to create a single factor that is sort of the total informed beliefs of the cluster. And some clusters might have no factors assigned to them, in which case this is a null product and is equal to 1. So now let's look at an example of a somewhat more interesting cluster graph than the trivial one that we showed earlier. Here we have a set of factors, phi 1 of ABC, phi 2 of BC, phi 3, phi 4, phi 6, etc. So initially we have to figure out for each of those factors a cluster in which to put it. For ABC, there's really only one choice, because there's only one cluster in this entire graph that understands about all of A, B, and C, and that's this cluster over here. BC, however, has two choices. It can go into cluster 1, or it can go into cluster 2, because both cluster 1 and cluster 2 understand about B and C. We're going to put it in cluster 2. I mean, we could have put it in either one. Both are fine. Phi 3 has, again, two choices. It can go into cluster 2, or it can go into cluster 3. We're going to go ahead and make the decision to put it in cluster 2. Cluster phi 4 has only one choice, because only one cluster has both D and E in its scope, so it goes here. Phi 5, similarly, only over here. BD, again, there is more than one choice. We can put it in cluster 2, or we can put it in cluster 3. Let's, for simplicity, put it in cluster 3, and BDF, only one choice. This is one possible way of assigning the factors to clusters. There's other alternatives, as I said, that would work. If we do this, we end up, for example, with psi 2 being the product of phi 2 times phi 3. Whereas psi 1 is simply equal to phi 1. And psi 3 is equal to phi 6 times phi 7. Here is a different assignment of the same factors to the clusters, and we can see that it's also equally legitimate. Okay, this was one cluster graph for those set of factors. Here's another cluster graph. So let's compare them. 1, 2, 1, 2. For the exact same set of factors. And notice that in fact the clusters haven't changed. What's changed is the edges and the subsets between them. Different cluster graph. Okay, so now let's think about message passing in the context of this more richly structured cluster graph to see what it looks like here. So here, for example, if we're interested in passing a message from cluster 1 to cluster 4, we're going to take psi 1, which is the set of factors that were initially assigned to cluster 4. We're going to take in the message that this cluster got from its other neighbor, 2. We're going to multiply them together, and then we're going to sum out all of the variables that 1 understands but 2 doesn't. So here, for example, 1 understands A and C, and 2 doesn't, so we have to sum out over A and C. And that is the message delta 1, 4. What about delta 4, 1? Delta 4, 1 is the message goes in the other direction. And here, notice that 4 gets messages from all sorts of other clusters. So in addition to its original factor psi 4, it gets a message from cluster 2, it gets a message from cluster 5, and it gets a message from cluster 3, each over its own scope. All of these are going to be multiplied together to give the current most informed beliefs about the variables B and E, which are then marginalizing over E, which cluster 1 doesn't understand, to produce a message over B. And once again, we know that the message from 1 is not used to inform the message that 4 sends back. So that gives us overall the following expression for message passing between cluster I and cluster J, so delta ij, over the scope of this, which is the subset, Sij, and that has the following general expression. It takes the factors initially assigned to cluster I, multiplies in all of the incoming messages other than from J, multiplies it all together, sums out the variables that cluster J doesn't know about. So everything that's in the scope of Ci, but not in the scope of Cj. And that gives us a factor over the subset that is produced as a message. So putting that together, that gives us an algorithm which is generally called belief propagation for the reasons that the clusters are propagating, if you will, informed beliefs to each other. And here is the summary of the algorithm. Each factor, phi, is first assigned to a cluster. That is used to construct our initial potentials, these psi's that we talked about. We initialize all of the messages before anybody starts communicating to be 1. And then we repeat the following process. We select some edge in the graph between adjacent clusters, and we pass the message between cluster I and cluster J over that edge. Okay? And we repeatedly, and this is the expression for that message. It's the one that we saw in the previous slide, and that process is repeated again and again. At the end of the process, a cluster needs to know what to believe about the variables that it understands. And so it takes it takes its own initial beliefs and all of the information that it got from all of its neighbors, multiplies it all together, and that produces these things, which are called beliefs. Now, there's several important aspects of this algorithm that are left undefined and that we're going to need to talk about later on. The first of these is repeat until when. When do we decide that we're done and that we can stop? And we'll talk about that in the context of different variants of this algorithm later on. The second thing that's left undefined is how I select each of the how do I select the edges? Which edge do I select to pass messages over? So here there's, the obvious simple things, which is just to go in some pre-specified order. And that's one option, is round robin message passing. But it turns out that there are better strategies than that, and we'll talk about that too. So is this algorithm any good? Well, it turns out that, yes and no. So first of all, if you pass messages over a graph like the one that I showed before, like the, little ABCD loop, eventually you see that we achieve convergence. So this is, here we can see that eventually we do converge to some probability, but that probability is a little bit off. That is, the answer is not exact. So in general, with exceptions that we'll talk about, this is an approximate algorithm, which shows that there's no free lunch. If the problem was NP hard, it's not like I have an easy way of solving it. So given all these problems with the belief propagation algorithm, what makes us think that it's an effective effective algorithm to use. When the algorithm was, and that produced talk about, the second thing that's left undefined is how I select each of the how do I select the edges? Which edge do I select to pass messages over? So here there's, the obvious simple things, which is just to go in some pre-specified order, and that's one option, is round robin message passing. But it turns out that there are better strategies than that, and we'll talk about that too. So, is this algorithm any good? Well, it turns out that, yes and no. So first of all, if you pass messages over a graph like the one that I showed before, like the little ABCD loop, eventually you see that we achieve convergence. So this is, here we can see that eventually we do converge to some probability, but that probability is a little bit off. That is, the answer is not exact. So in general, with exceptions that we'll talk about, this is an approximate algorithm, which shows that there's no free lunch. If the problem was NP hard, it's not like I have an easy way of solving it. So given all these problems with the belief propagation algorithm, what makes us think that it's an effective algorithm to use? When the algorithm was rediscovered in the 1990s, 1990s, Murphy, Weiss, and Jordan, as well as others, looked at its performance in the context of real networks, and specifically networks that have a lot of loops, which is what causes the loopy belief propagation algorithm to misbehave. And so here's an example network. It's called the pyramid network. It's a network that is analogous to one that arises in image analysis. And what they showed is that when you compute on the one hand the exact marginals on the x-axis, and for different marginals in the network, and on the y-axis we see the marginals computed by loopy belief propagation, we see that the marginals by and large sit almost exactly on a straight line with few exceptions, showing that the loopy belief propagation is very close to accurate on this network. Here's another network. This is a simplified version of a medical diagnosis network. And once again, we can see that when we compare the correct marginals on the x-axis to the belief propagation marginals on the y-axis, the marginals sit almost exactly on this straight line, which shows that, again, they're very close. The belief propagation is very close to accurate. So to summarize, the belief propagation algorithm passes messages over a graph of clusters that are connected to each other via subsets. The adjacent clusters pass information to each other in these messages, transmitting information only about the variables in the subset, which are the ones that they have in common. The message that cluster I sends to cluster J summarizes everything that I knows about the variables in the subset, except for information that it obtains from J, so that one avoids direct double counting of the same piece of evidence where J gets his own information back again via I. We've seen that the algorithm may not converge, and it can have this oscillatory behavior, and that the resulting beliefs are pseudo-marginals in that they are not necessarily the exact marginals from a theoretical perspective. But nevertheless, as we've seen, the algorithm actually performs quite well in a range of practical applications, which is why it's quite commonly used. We described the belief propagation algorithm as passing message over a cluster graph, but we left unspecified how that cluster graph would be constructed and what properties it needs to satisfy in order to support reasonable message passing. So let's remind ourselves what cluster graphs are. A cluster graph is an undirected graph whose nodes are clusters that involve subsets of variables, and edges involve a subset Sij, which is a subset of the two clusters on the two endpoints. What are some properties that the cluster graph has to satisfy? The first property is one called family preservation, an obvious value, where remember that we need, given a set of factors phi, we need to be able to assign each phi k to some cluster. C alpha k, such that the cluster can accommodate the scope, so can accommodate phi k. Accommodate. Well, in order for the cluster graph to allow this to be done, we need to have an appropriate cluster in the cluster graph. So this imposes a constraint on the cluster graph that says that for every factor phi k in my set of factors phi, there exists some cluster Ci such that Ci accommodates phi k, which means that you can put phi k inside this cluster. That's the family preservation property. The second property is a little bit trickier to understand. It's called the running intersection property. The running intersection property, let's first read the definition and then understand what it says. It says that let's assume that we have a pair of clusters, Ci and Cj, and a variable x that belongs to both of them. So for example, we might have the variable x sitting here in C7 and the variable x sitting here in C5. This property says that there exists a unique path between Ci and Cj for which all clusters and subsets along the path contain x. What does that mean? It means that, for example, should I choose this to be my unique path, it means that x needs to sit here, here, and here. So there is a connecting path that involves x, and that path is along the entire route, and that path is unique. So let's try and understand the intuition between both sides of this definition, the existence and the uniqueness. Imagine that let's do the existence first, and imagine that for whatever reason I decide that there is not going to be a path over here. So there is no way for C7 to communicate to C3 about the variable x. Well, that means that we now have these two separate, isolated communities, each of which has some information about x, and they can never talk to each other about x. So they're never going to get to agree about x. There's never going to be any information transfer of these two pieces of information. Well, so that's not very good, which is why we need that path to exist. Okay, so that's the exist part. What about the unique part? The unique part is a little bit trickier to understand, but let's try and provide some intuition for it. Let's imagine that I have two paths that involve x. Well, so now let's think about this message passing algorithm. So C3 can send a message to C5 with information about x. For example, I think x is taking the value 1. I have a factor that suggests that x takes the value 1. Well, C5, integrates that with its own information and sends it on to C2, which sends it back to C3. And now C3 hears from C2 that, ooh, x needs to take the value 1. That reinforces its beliefs that x needs to take the value 1, and so the probability goes up. It now goes back and sends that information on to C5, which sends it on to C2, which sends it back to C3. And then, once again, the probability in x taking the value 1 goes up. And so we have this sort of self-reinforcing loop that's going to give rise to very extreme and very skewed probabilities in many examples. And so a way of avoiding that is to, or at least reducing that risk, is to prevent these kinds of feedback loops. Now, it's important to realize that by preventing these loops, that only reduces as opposed to eliminates the problem. And specifically, this is kind of a little bit of a digression, but it's important to know, is that imagine, for example, that we have x and y that are very strongly correlated. So here we have, for example, x and y. And here we have a path that involves y. Okay? So now what's going to happen is that C3 sends information to C5 about x. C5 translates that to information about y. Y should take the value 1. That information about y goes back to C3 and increases the probability in x taking the value 1. Now, this is a little bit of a forward-looking hint about some of the issues that we'll see with belief propagation later on, which is that belief propagation does very poorly when we have strong correlations. And that's because of these feedback loops. So the more skewed the probabilities in your graphical model, the harder time belief propagation has in terms of the results that it gets. So with that digression aside, let's go back to the running intersection property, and let's provide an alternative definition of the running intersection property just to give ourselves some additional intuition. The running intersection property is equivalent to saying that for any x, the set of clusters and subsets that contain x form a tree. So for example, if we have x here, 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 and here, we can see that the set of clusters and subsets that contain x form a tree. It has to be connected because of the existence of a path, and it can't be a non-tree because that would give us two different paths. And so that's a different view of this. And so you can think of each variable inducing its own little tree across which information about that variable flows in the graph. So now let's go back with that definition and consider some cluster graphs that we might adopt for this example that we've seen before. So here we have our 5 clusters, and let's check whether it satisfies the running intersection property. We've already done family preservation for a particular set of factors. So let's consider, for example, the variable b, and we can see that we have b here, 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 and here. And we can see that that's a tree. Here's my tree. Note very carefully that B isn't here. If B were here, that wouldn't satisfy the running intersection property. That would be an illegal cluster graph. It's actually on a subsequent slide. Here is an illegal cluster graph. It violates the running intersection property. Why? Because here is B, and here's a bunch of other B's. And there's no way to connect cluster 2 to any of the others. So this one violates the existence. This one, which we just talked about, violates the uniqueness. Because here we have all of the clusters and subsets that involve B, and there's this nice little loop over here that has 2 paths between, say, cluster 1 and cluster 4. If we wanted to take the cluster graph and still allow communication between B and C, so we want to have, for example, we want cluster 1 and cluster 2 to be able to transmit to each other information about how B and C are correlated with each other, which they can't do in this graph over here. So one way to do that is we have eliminated, in this case, this edge that we had over here that involved B. And now, once again, we have B being a tree in the graph. Now, I've focused on B here, but it's not difficult to convince yourselves that other nodes also satisfy, that we satisfy the running intersection property also with respect to other variables. So just as an example, here is the set of clusters and subsets involving D, and that too is a tree. And here is the ones involving E, and that too is a tree, and so on. So, and running intersection property needs to hold for every one of the variables. How do we construct a cluster graph that has the desired properties? One, very simple, and in some ways degenerate, but still, because of its simplicity, very often used, is a cluster graph called the beta cluster graph. And that's a term from statistical physics where people use this kind of approximation to energy functions in some calculations in statistical physics. So here we have, in the beta cluster graph, we have two types of clusters. We have big clusters and little clusters. The big clusters, these are the big clusters, correspond to factors in phi. So for each phi k, we have a cluster, a factor cluster, whose scope is exactly the scope of phi k. That's the big clusters. The little clusters correspond to individual variables. So for each xi, we have a cluster whose scope is just a single variable, xi itself. Now, we're going to connect ck to xi exactly when xi is a subset of ck, is a member of ck. So if we consider the set of factors that we had before, we can now produce a different cluster graph than the one that we had previously. This is a beta cluster graph. Notice that we have these big clusters. These are these these five. And we have these little clusters corresponding to A, B, C, D, E, and F. And we can see that we have an edge, for example, between the ABC cluster and the A cluster, the B cluster, and the C cluster. And that's how messages are passed. And you can see that this graph is degenerate in the sense that it only allows information about singletons to be passed. It loses in every message passing step any information about the correlation between variables. But nevertheless, it's simple to construct, and it's guaranteed to satisfy the running intersection property. Why is that? So let's consider, for example, all of the factors that involve the variable d. So here is, what are the clusters that involve the variable d? Well, there's this one, and then there's this, that, and that. Those are the where we have the subsets, which I didn't mark, and then these ones. And notice that it's a tree by definition, because d doesn't appear on any other subset except these ones. And so the tree is a star. It's the variable cluster plus the big factors that contain the variable. So D, and in this case, the three clusters that contain it. So to summarize, we looked at the properties of the cluster graph, and we see that there's two of them that it needs to satisfy. The first is family preservation, which allows the set of factors to be encoded. And the second is the running intersection property, which serves two purposes. The first is to connect all information about any single variable so that it can all be transmitted through the graph, but without creating tight feedback loops that are going to give rise to this self-reinforcement and highly inaccurate answers. The beta cluster graph is often the first default that people use because it's easy to define and it's guaranteed to be correct. But richer cluster graph structures of the type that we talked about can offer very different and sometimes significantly better trade-offs with respect to, on the one hand, the computational cost, and on the other hand, which of course, as you start increasing the amount of the sizes of the messages that are passed, that can grow more expensive, but at the same time, allow us to improve the preservation of dependencies as messages are passed in the graph so that more information is actually kept and not lost in this message passing process. So now we're going to look more closely into the belief propagation algorithm and understand some of the important properties that it has. So here's our example cluster graph with the 4 clusters over the loop. And now let's remind ourselves that the cluster beliefs are defined to be the product of the factors assigned to the clusters, psi1 up to psi4, times the product of the messages that were incoming into the clusters. So for example, the beliefs over cluster 1 is psi1 of AB times the message coming in from cluster 4, whose scope is A, and the message coming in from cluster 2, whose scope is B. Now, a cluster graph is said to be calibrated if the clusters agree with each other. So specifically, if in terms of their beliefs, beta I, if we were to ask cluster 1 what it thinks about, say, a variable B, and we were to ask cluster 2 what it thinks about the variable B, they would agree with each other. Formally, this says that if we marginalize out the belief at, say, cluster I, and marginalize out the beliefs in cluster J, and we ask them what they agree about their joint subset, Sij, they would agree with each other in terms of the marginal beliefs. Now, an important property of cluster graph belief propagation is that convergence of the belief propagation algorithm implies calibration. So to understand why that's the case, let's go through a simple derivation. So the convergence of belief propagation occurs when the message at the next time step equals the message at the previous time step. So now let's see what the implications of that are. So if this is the message at the next time step, it's computed as the product of the psi i's, which are the factors assigned to the cluster I, times all of the messages other except for cluster J. And those are all multiplied together and marginalized out over the subset. So now let's remind ourselves of what the beliefs would be at this point in the process if we were to compute them. And that's derived from this expression over here. So this is the same psi I that we had over here, and this is the product of all messages. So if this is, if here we have the product of psi I and all messages except one, and here we have psi I and all messages, we can equally well rewrite it in this form over here where we multiply in all of the messages and then divide out the one that wasn't included, delta Ji. So now, because of convergence, we have that this is equal to delta ij because of this equality over here. And so if we rewrite that, we can see that we have that delta ij times delta ji is equal to this summation over here, because we can multiply delta ji on the right-hand side by delta ij on the left-hand side. So we have shown that delta ji times delta ij is effectively the marginal over the beliefs at that point in the process. But we can equally well, using the identical argument, show that delta ji times delta ij is also the marginal over the beliefs for cluster J. So if this is the beliefs for cluster I, this is the beliefs for cluster J. But we've shown that in both cases, the marginals are equal to the same expression, which is the product of the messages on both sides of the link. And so, because both expressions are equal to the same thing, they must be equal to each other. And this is exactly the calibration property that we were trying to prove. So we've shown that convergence of the belief propagation algorithm implies calibration. This expression, which corresponds to the subset beliefs, because it's the marginal over the cluster beliefs, is called mu ij, and it's an expression that we'll use a little bit later. In particular, one of the important properties that we get by putting these pieces together is another property called reparameterization. Now that's a bit of a mouthful, so let's first do the derivation and then understand what the word means. So remember that as we run belief propagation, at the end of it we have these beliefs over the clusters, which are defined in this expression. So specifically, for example, we have, for cluster 1, we would have psi 1 times delta 4 1 times delta 2 1, and similarly for the other clusters. We've also just now defined these subset beliefs, which we've just shown are a product of two messages on the two different going in each direction. So specifically here we would have, for example, that mu of 1, 2 is equal to delta 1, 2 times delta 2, 1. Now if we look at this graph with all these little factors attached to the clusters and the subsets, we see that there's a lot of repetition here. So delta 4, 1 appears, for example, here, but it also appears there. And in fact, if we look at it, we see that each of these message expressions appears exactly twice. So delta 4, 1 appears here and here. And for example, delta 1, 2 appears here and here. And so if we write all of these together in in a different form, we can see that if we multiply all of the beliefs and divide by all of the subsets, we would end up with multiplying in delta 4, 1, for example, on the belief side, but then canceling it out when we divide by mu 1, 4. And similarly, delta 1, 2 would be multiplied in terms of beta 2, but then canceling out in the denominator in mu 1, 2. So if we wanted to write this in a little bit of a broader setting, so if we have a product of the beliefs over here multiplied and then divided by a product of all of the subsets, we can see that this numerator is equal to the product over I of psi I times the product of all of the incoming messages into clique I. The denominator is simply equal to the product of all of the messages on each direction. And we can see that here we're just counting the same message in two different ways. And so each message appears once in the numerator and once in the denominator, which means that they all cancel with each other. And so what we end up with is the product of all of the initial potentials psi I. And that product is simply the unnormalized measure. And so the implication of this is that this expression over here, this ratio, is simply a different set of parameters that captures the original unnormalized measure that defined our distribution. And so we haven't lost information, no information loss, as a result of the belief propagation algorithm. The representation of the unnormalized measure is still there, just using a different set of parameters, specifically the cluster subsets, the cluster beliefs and the subset beliefs. So to summarize, we've seen that at convergence of belief propagation, the cluster graph beliefs all agree with each other on the variables that are shared among them. And as a consequence of that, the cluster graph beliefs are simply an alternative parameterization of the original unnormalized density, but one that has this nice calibration property, which allows us to read off information about a variable from any clique in which it appears. And so we have reparameterized the original distribution into a more convenient and easily usable form.